All right, has anyone looked at the conservation of linear momentum problems yet? Anybody have any questions about those? Joey, you look at those problems right now. But no one has any questions on those. I think the linear momentum ones will be pretty straightforward. They're pretty much like the examples. So we're going to get into the next thing, which is conservation of linear momentum. So this is still part of conservation laws, but we're going on to the second and last conservation law. Wait, conservation of mechanical energy, is that what I said? Okay, that was stupid. Conservation of mechanical energy. So conservation of mechanical energy is a simplification, like a special case of conservation of energy. Conservation of energy always holds. You know, energy, all it can do is change type. But in certain cases, where you don't have any thermal energy, any electrical energy, that kind of stuff, you can simplify it into this form. So thermal energy, like for example, in a car engine, you know, you have chemical energy in the form of gasoline that goes into the cylinder, and then you ignite that gas to release the potential energy in the chemical energy, and it makes the gas in the cylinder expand, and that makes the piston rise. And so that's all, you know, there's all these types of energy, but that's an example of thermal energy and an example of chemical energy. And we're going to be dealing with cases that don't have any of that kind of stuff. Okay, so I'm first going to start by just giving you like a definition of conservation of mechanical energy. Usually I do it in the reverse way. I define all the stuff and then we finally work our way up to, but this time I want to start with conservation, with like the law, you know, and do an example problem showing how simple most of these problems are going to be mathematically, and then go into the more complicated stuff, which is understanding when you can use this and what the different parts mean and stuff like that. Okay, so if so this is the conservation of mechanical energy law. If the only forces that do work, so there's the first word that you haven't seen yet. If the only forces that do work on an object are conservative forces, so there's the second term you haven't heard yet. Then the potential energy plus the kinetic energy of the object is a constant. And we also haven't talked about potential energy. And we haven't talked about kinetic energy. So there are 4 terms here that I'm going to need to introduce. Work, conservative forces, potential energy, and kinetic energy. But before I do that, I'm just going to lead you through an example problem so you can see, like, it's hard to talk and write. Example. So we're going to go through a problem where until now, we haven't had the ability to solve this problem in any way. And you're going to see it's such a short, easy calculation. And so this is going to give us a lot of new ability to calculate stuff. but it does have some sort of subtleties that we'll have to get into. So, okay, let's imagine swinging a ball on a string around in a circle. Okay, and let's say that the length of the string is 0.2 meters. And at the top of the circle, let's say that the speed of the mass is 5 meters per second. What's the speed at the bottom of the circle? Yeah, we haven't been able to use Newton's second law for this. With integral calculus, you could use Newton's second law to calculate this, but it would take a long time. You know, it would be sort of a difficult calculation. We don't have a way to do it without calculus. You couldn't use constant acceleration equations, but it's going to be really quick and easy with conservation of mechanical energy. So the potential energy due to gravity has the form mass of the object times g, 9.81 meters per second squared, times the height of the object. And I'm going to usually denote potential energy as capital U. And the kinetic energy of an object is always going to be 1/2 times the mass times its speed squared. And I'm going to denote that with a capital T. And so here's what we're going to do. I'm going to write out like a little table with one column for instant 1 and one column for instant 2. I'm going to call instant 1 when the object is at the top of the circle, because we know some stuff there. And then instant 2 is going to be at the bottom of the circle where we're trying to calculate this speed. And then I'm going to calculate the potential and kinetic energy at both of these two instants. Okay, so first of all, at the top of the circle, we have m, the mass of the object. It turns out that that's going to cancel out, so we didn't need to know the mass of that for this problem. Sometimes you do. And then g, remember, is 9.81 meters per second squared. And then we need the height of the object at the top of the circle. Well, it turns out that, because what does it mean to come up with the height? Like, you need a reference point to come up with the height. So is the reference point for us, I mean, here are a few possible, seem reasonable ideas of how you measure height. It could be from the bottom of the circle. It could be from the ground. It could be from the center of the earth. It could be from the sun. You know what I mean? So what do we mean by height? It turns out that you can choose any point you want as your reference height as long as you're consistent through the whole problem. So I'm going to call the bottom of the circle my height equals 0 and just measure all the heights from there. Okay? So if the bottom of the circular path of this object, so down here is what we're calling height equals 0, what's the height of the mass at the top of the circle? 0.4. Yeah, 0.4. Do you see that the string is the radius of that circle? And so you need 2 times the radius to give you the diameter. And so the potential energy comes out to be 3.924 times the mass. And now what's the kinetic energy at the top of the circle? That's 1/2 times the mass times the speed squared. The speed was 5 meters per second. And so this is 25 divided by 2, so 12.5 m. And then we'll go to the bottom of the circle. The gravitational potential energy is the mass times 9.81 times what's the height at the bottom? Yeah, that's what we're choosing as our zero height, so this comes to be 0. And then the kinetic energy is 1/2 times the mass of the object times its speed squared, and the speed is what we're trying to calculate. So I'm just going to leave this as v squared, and we're going to calculate that v. Okay? And now we'll put this into the formula, add up potential and kinetic at instant 1. That has to be the same as the potential plus the kinetic at instant 2. Now you can divide both sides by m, and so the m disappears, and what that tells us is that the answer here is the same no matter what that mass is. And we get that v squared is equal to 32.85. Take the square root of both sides, and you get that the speed is equal to square root of that, 5.73 meters per second. Okay, so as far as using conservation of mechanical energy, as far as the math of it, this is about as complicated as it ever gets. But now we're going to spend the rest of today and some of the next class just defining these different terms and figuring out how to interpret this stuff and like that.
Why did you cancel both ends and not just one of them?
Oh, well, you can write this as, like I could have written this as 3.924 plus 12.5 all times m, you know, and this one is 1/2 mv squared. And then you can see that now I'm just dividing an m from both sides. Yep.
Can you scroll up to the two equations again?
Yeah. Let me delete this. These two?
Yeah, I just need the
Okay.
GH.
Yeah, I'll get this stuff all entered. You know, that was a very like whirlwind introduction to how to do these calculations. But I just wanted you to notice that like once we've put all the ideas in place, this is what you're going to do in a problem, you know, and it's not very much. But now I'm going to spend 2 days just trying to help you understand what these different things mean, you know. Any other questions about this? Okay, so now we're going to go back and define kinetic energy, work, conservative forces, and potential energy. So I'm going to start with kinetic energy. That's the most straightforward one. For a particle, so now this is assuming that we're talking about objects where we can treat them as having no length dimensions and that we're not worried about the changing orientations. Because there's also kinetic energy for spinning of objects that are not particles, but we're not dealing with that yet. And this is capital T. The kinetic energy is 1/2 times the mass of the object times its speed squared. If instead of having the speed of the object, you have its velocity vector, it's easy to calculate the kinetic energy from that too. So if you have the velocity vector v instead, then the kinetic energy is 1/2 times the mass times the quantity, x component squared plus y component squared. The SI units, so these are the SI units for kinetic energy and also any other type of energy. So R, well, think about what the formula says. What are the SI units for mass? Kilograms. What are the SI units for speed? Meters per second. And if you square meters per second, you get meters squared per second squared. So the SI units for energy are kilogram meters squared per second squared, which, because remember newtons is this sort of, we gave the name newtons to kind of a complicated combination of units, kilogram meters per second squared. So this also is the same as newtons times meters. And because we're going to use these units a lot, we gave this its own name, joules. And we abbreviate it with a capital J. There are a few things I want you to notice about kinetic energy. The first one, okay, so when we talked about linear momentum, was linear momentum a vector or a scalar? Was it a number or a vector? Vector, right. So linear momentum has direction. Kinetic energy is a scalar. So kinetic energy, like all energy, so this is true of every type of energy, is a scalar, not a vector. So it doesn't have any directional information. Linear momentum, say, has a magnitude of kilogram meters per second and a direction towards the door or something, you know. Energy doesn't have that. It only has a magnitude. The second thing I want you to remember is that the meaning of kinetic energy, like the intuitive meaning of it, is similar. It's not the same, but it's similar to the magnitude of linear momentum. Anybody remember the definition of linear momentum? It's the mass of the object times its velocity. So the magnitude of linear momentum is mass times speed. Okay, so the same two things go into kinetic energy as go into linear momentum magnitude, mass and speed. It's just that for kinetic energy, we square the speed. Okay. So just like linear momentum, you can think of higher kinetic energy as meaning the object is harder to stop. Okay, so a train going full speed has a lot of kinetic energy. A ladybug going full speed has a small mass and a small speed, so it has very little kinetic energy. And so, you know, if somebody asked you, we have to stop two things, a train and a ladybug, you could quick do this calculation of kinetic energy and then say, like, I'll stop the ladybug, you stop the train, you know? And then the third thing, I mean, this is kind of, this is important to remember. It's kind of implied by some of the other stuff I said. But as an object speeds up, its kinetic energy increases. Usually, when you're doing a calculation for a single object, you don't have any control over its mass. You know, the mass doesn't tend to change. There's some cases where that's not true, but for the most part, the mass is fixed, but the speed changes over time. So like if somebody asks you, you know, how much kinetic energy does a train have? Well, it varies. If it's stopped, it has zero kinetic energy, you know. You'd rather stop a stop train than a ladybug going full speed, you know. Those can sting. Okay. So that's kinetic energy. Anybody have any questions about that? The next thing that we need to talk about that I need to define is work. And work is energy added or removed from an object by the application of a force. The fact that it's added or removed by the application of a force is important here because there are a lot of ways to add or remove energy from things. You know, like a cup of water, you're adding energy to the water if you hold it over a flame, you know, and you, but that's not work that you're doing to raise the to raise the energy of the water. That's applying a temperature difference. Okay, so that's a different thing. We're just talking about energy added or removed by applying a force to it. To calculate, so energy is added if the work is positive, and it's removed if the work is negative. Okay. To calculate the work done on an object, between instant 1 and instant 2. By a force F. So remember, forces are a vector, so by this force vector F. First, calculate the displacement of the object as time goes by from instant 1 to instant 2. So remember, the displacement is the position of the object at instant 2 minus the position of the object at instant 1. The position at the later minus the position at the earlier. Then the work is the x component of the force times the x component of the displacement vector plus the y component of the force times the y component of the displacement vector. Sort of a funny new calculation that you haven't seen before, but I'll sort of try to give you a sense of what this means. By the way, this is denoted, this kind of calculation is denoted, get that dot out of there, that doesn't go there. F dot D, and this is called the dot product. And it's something that comes up in physics and engineering a lot. So I'm going to write out an example with objects moving certain directions, forces going certain directions, and we're going to start to get a sense out of how this calculation works, what it does, okay? So for this example, let's say that we have a car, and let's say that this car, in every one of these examples, is moving from this position at 1 to this position at instant 2. And the coordinate system we're going to use is like this, with the origin at position 1 and that orientation. And let's say the car is going this way. And while the car goes from position 1 to position 2, let's first, so like part A here, let's say that you apply a force to it in this direction. And let's say that that force is 1,000 newtons. And we'll say that the distance between these 2 points is 10 meters. All right, well, let's first calculate the coordinates of these points P1 and P2. What are the coordinates of P1?
0, 0.
Yeah. What are the coordinates of P2? Perfect. And what are the components of that force vector?
1,000, 0.
Yeah, 1,000, 0, right. And now that we have these, our displacement vector is going to be P2 minus P1. So that's 10, 0 minus 0, 0. So you get this. And now we can finally calculate the work. The work is equal to Fx dx plus Fy dy. So that is 1,000 times positive 10 plus 0 times 0. and that's positive 10,000 joules. Okay, so there's the calculation. Now let's make sense out of the fact that this work is positive. Okay, well, the car is moving from P1 to P2. If you apply a force in the direction that something is moving, do you speed it up or slow it down? You speed it up, so you would expect the kinetic energy to increase. And so that's what we got here. The force increases the kinetic energy by speeding the car up. That doesn't mean that the car does speed up, because as far as we know, there could be 100 other forces slowing it down, you know. But it says that that force is doing everything it can to speed this thing up. Okay? And so that force is adding energy to the car. Anybody have any questions about that interpretation? So now let's think of, you know, similar example, but now we're going to have the force going the other direction. So again, we have P1 and P2. These are 10 meters apart. Coordinate system is here. But this time there's a force on the car going this direction with a magnitude of 1,000 newtons. Well, let's think of it in the other order this time. So if you have a car that's going to the right and you're applying a force to the left, is that force increasing the speed or decreasing the speed? Decreasing. So you would expect this to have a negative work because you expect this force to decrease kinetic energy. So let's see how that works. So the displacement vector, again, is 10, 0. We didn't change that. The force vector this time is negative 1,000, 0. And so the work is negative 10,000, negative 1,000, sorry, times 10, plus 0 times 0. And that gives you negative 10,000 joules. So the force decreases the energy by slowing the car down. Well, again, remember that that isn't saying that the car is actually slowing down. It's just saying that if this force had its way, the car would slow down. You know what I mean? So this, in this case, could represent the air resistance on the car. Well, you have an engine in your car, so you can overpower that air resistance. But the effect of air resistance is to decrease the energy of the car. If that force wasn't there, the car would have more energy. Okay? And then the last example. Actually, let's do one more after this. But what do you think the third example is going to be here? So I'm just changing the direction of the force. What direction do you think the force is going to be? Yeah, exactly. Up or down, yeah. It's going to be perpendicular to the displacement. We did one that was in the same direction as displacement, one that was opposite. So now we're going to do one that's perpendicular. That was such an unnecessarily contrary. Okay, so that distance is 10 meters. Now let's do, sorry, I'm going to go with Lisa, no offense. I'm going to make this force down. And the coordinate system is here. Well, if you ignore, so there might be sort of side effects of this downward force, like if you push down on something that's sliding, it increases friction. There could be some effects like that, but we're not thinking about stuff like that. That's separate from this issue. We're assuming that the only thing we care about is this force that's perpendicular to it. So what would be the effect if you have something rolling along the ground and you're just applying a force exactly perpendicular to that motion? What would you guess that does to the speed of the car? Yeah, so when you say it would slow it down, that's because of your intuition about basically friction. But we're gonna forget about that. And so the effect would be, if there was zero friction, which is hard to imagine, the effect would be that the speed stays exactly the same. It doesn't have any effect on the speed. Okay, so let's do this calculation and see how that works. So the displacement, again, is 10, 0. The force vector, this is in the negative y direction, so 0, negative 1,000. And so the work done by this force is Fx times dx plus negative 1,000 times dy, 0. And so we get a work of 0.
Instead of speed, then it normal direction change?
Instead of what?
Instead of changing the speed,
Oh, yes. So it would, so that force, if this thing was in space and wasn't on the ground, it would have the effect of changing the direction. But we have the benefit of saying, well, did it change the direction? It didn't, right? This thing went from P1 to P2. So we don't have to worry about stuff like that. So this does 0 work. That means that it doesn't contribute to changing the energy of this car at all. So there's no energy change because it doesn't affect the speed. All right, what if you had a force vector that wasn't parallel or perpendicular to the displacement vector? It could be at some kind of angle. So let me just do one like that. So here's P1, P2, the car still does the same thing. But now let's say we have a 1,000 Newton force that's like this, and let's say that this angle is 30 degrees. What does your intuition say about whether this force would speed it up or slow it down? It would speed it up some. It just wouldn't speed it up with the entire force vector, and that's exactly how it's going to work out. So our displacement is 10, 0. Our force vector is 866, and then negative 500. Yeah, that's 1,000 times the cosine and sine of negative 30 degrees. Because if you put your coordinate system here, put the tail of your vector here, and so then the work is equal to 866 times 10 plus negative 500 times 0, and you get an answer of 8660 joules. And that increases the energy, increases the car's energy. Okay, so now we've seen these 4 cases. Let me just sort of summarize the intuitive results that you should try to keep in mind as you do this stuff. So the intuitive result if the force and the displacement vector, actually, not the displacement vector. Let's think of it like this. If the force and the instantaneous velocity, so that's the direction it's moving at any instant, are within 90 degrees of each other, then the work is greater than 0 and the energy is increased by the force. So that's a case where, like, the force is going this way, the displacement vector, the velocity at that instant is this way. This angle is less than 90 degrees. In that case, the work is going to be positive. Second, if the force vector and the velocity vector are greater than 90 degrees apart, the energy is going to be decreased by the force. So that's a case where, like, the velocity is going this way and the force is like this. And that angle is greater than 90 degrees. And then the last one to keep in mind is, well, what do you think it's going to be? If F and V, what? Yeah, right, if they're perpendicular, if F and V are, oops, hold on. So if F and V are 90 degrees apart, then work is equal to 0, and there's no energy change due to that force. All right, so that's the idea of work, and you can sort of see how work relates to kinetic energy. Unfortunately, Calculating the work is usually difficult to do. It's usually difficult to calculate the work. It wasn't difficult in the ones we did, but that's because we assumed that that force was constant the whole time. But in general, forces are changing as time goes by. And so if that force is changing, there's really nothing you can do here. There's something you can do with calculus, but for us, we're kind of out of luck. There is an exception, though. When forces are conservative, the work they do can be calculated using potential energy. And we're going to call potential energy capital U. And the relationship between work and potential energy is this. The work done by a conservative force is negative change in potential energy. Okay, so that's how this idea of certain kinds of forces that we call conservative forces is like sneaking into this idea of energy and whether the energy is increasing or decreasing. Okay? All right, so now we're at this point, we need to define conservative forces and potential energy of conservative forces. So a conservative force, so a force is conservative if knowing the object's location is enough to specify the force. So we know a lot of forces that do fit this and a lot that don't. So let me give you some examples of how this works. All right, so the key thing is in the application of this force, so say we're talking about forces applied to this calculator. If I tell you the location, and say you know the mass of the calculator, okay. If I tell you the location of this calculator, is that enough information? Is there only one possible force that could be applied at that location, basically? Okay, so gravity, let's think about gravity. So say this has a mass of 0.1 kilograms. If I tell you that this calculator is at this location, is that enough to know the force that gravity applies to it? Yeah, and actually gravity is, the way we've been talking about gravity is even a little stronger than that. We don't even have to know the location, but the location is enough, more than enough. So if I say this is here, then you say, yes, I know the force is directed down and it has a magnitude of 0.1 times 9.81, okay? And there's no example, no matter what it's doing, moving, which way it's going, there's no example where that isn't the force at that location. Okay? So gravity is a conservative force. And that's good news because, you know, we're saying that this idea of energy is going to be easy to use for conservative forces, and gravity is the one force that shows up all the time. And now we know that that's going to be relatively easy to deal with, you know? So let's think about another force, like what about the pushing force that this cable applies to the calculator? That's a little bit of a tricky one because you might think like, oh, well, you know, the way you're thinking about it right now, gravity is pushing that way, pulling that way. The table is pushing opposite, and they're offsetting each other. So you might think, yeah, if it's here, the table is applying this force to it. But what if I like push on this, you know? Now the table is applying a bigger pushing force to keep this from sinking into it. I didn't change the location, but I changed the pushing force from the table. So the normal force from the table is not conservative, okay? And actually, this is probably an easier one, but what about friction? Is, like, if the location is there, do you know the friction force on it? Right, you don't know it. If it's sitting there like that, the friction force is 0. If it reaches that spot sliding this way, we know the friction force is opposite that velocity. If it reaches that point sliding this way, we know the friction force is that way. So there are all these different friction forces it could have.
So if it's variable, we can't be concerned.
Right, if there's more than one force that could be applied with that object at a single location, then you know it's not conservative. Anyone have any questions about that? The good news is for this class, it doesn't take too much thinking about it because I'm just going to give you a list of conservative and non-conservative forces that we'll deal with. One other sort of interesting thing, some people might find it interesting, is conservative forces are forces that you can think of as a force field. Like when I was a kid, like all the shows had force fields and like it meant like this invisible thing that you could, but real force fields are boring. It just means that the idea of a force field, you know, like a field of daisies. Like what is a field of daisies? It's a field, it's a place where every single location you go to, there's a daisy there, you know? And so that's the idea of a force field. Everywhere you go, there's kind of like a force waiting for that object there. Okay, so as you move this around, you can think of there being like latent gravity everywhere. And when this gets to this one spot, it activates this one force of gravity there. So that's why they call it a force field, I imagine. And for any conservative force, you can think of it in terms of a force field. So like when people talk about electric fields or magnetic fields, that's what they mean. Those are conservative forces where there's a force waiting at each location for the object. Okay. Every conservative force has potential energy. So conservative force examples. Are the weight or gravity. Another example is an object that's attached to a spring. So the force that a spring applies to an object is conservative. So if you have one end of a spring attached to the wall here and the other attached to this object, and you pull the object this far, there's only one force that spring can apply to the object, trying to pull it back to its resting position. Okay? And no matter where the spring went before that instant, that spring force at that instant here is the same. Okay? So these are conservative force examples, the only ones that we're going to do in this class. Non-conservative force examples. Friction is one. Normal forces are another one. Cable forces are another one. And these go on and on. So in this class, the only two conservative forces we're going to deal with are gravity and spring forces. We're going to assume that everything else is non-conservative. So for these conservative forces, I probably could have organized this better, but the potential energy functions that you're going to need to know for this class first, you'll need one for gravity, and we already used that in that first example. So the potential energy due to gravity is the mass of the object times g, 9.81 meters per second squared, times the height. The second one is for springs. 1/2 times the constant k times x squared, where k is the spring stiffness. It tells you how easy or hard it is to stretch out the spring. And x is the distance from the spring's resting length. So the more you deform a spring from its resting length, the more potential energy it has. Okay? And you can think of potential energy as like the strength waiting in that spring to return it back to its resting length, for a spring. All right, so if those are the only two conservative forces that we're going to deal with in this class, your first thought might be like, wait, we can only do calculations using energy where the forces are applied by springs or by gravity? That limits the kind of problems you can do pretty extremely, Well, we know that that's not the case actually from this first example up here, because notice that in this ball swinging around, that ball, gravity is acting on it. So, okay, that's a conservative force. But there's also this cable force acting on it. And I already listed that in my list of things that are non-conservative forces. So why can we apply this conservation of mechanical energy in the case where there's a string cable force? So remember what we said about, so in this take-home message, the intuitive result of our discussion of work said that if the force and the velocity at every instant are 90 degrees from each other, that force does zero work. Okay? And the rules for using conservation of mechanical energy say, it doesn't say that the only forces are conservative. It just says that the only forces doing work are conservative. Okay? So, there are two very important non-conservative forces that do zero work. So two important forces do zero work, and the reason that they do zero work is that the force they apply is always 90 degrees from the velocity vector. The first one of these is a normal force in rolling and sliding. Okay, so if you have an object that's rolling or sliding, and its velocity is, along the surface, what's the direction of the normal force? It's always perpendicular to that surface, and those two forces are perpendicular. And the second one that we're going to use a lot is centripetal forces. That means forces toward the center of a circle during circular motion. So if you have an object moving around a circular path, say the object is here at this instant, its velocity vector is tangent to the path. A cable force, like holding this in this circular path, for example, is toward the center. And so these two are always 90 degrees apart. So we can do any problem. Let's say it like this. We can use conservation of mechanical energy for any problem involving gravity, springs, normal forces in rolling or sliding, or centripetal forces in circular motion. Okay? So I'm going to box that. That's kind of the final word on what kind of problems we can do. And I'm going to do one more example, and then we'll be done for today. So let's say we have a little hill. Let's say that this hill has a height of 3 meters. That doesn't say how long, like how far it would be if you pulled a tape measure along the ground. That just says the change in height of this hill. And let's say you have a skateboarder at the top of the hill. And if the person is at rest at the top of the hill, how fast will the person be at the bottom of the hill? The first thing you have to do is think about whether you can use conservation of mechanical energy here. So let's think about a free body diagram of the skateboard at some arbitrary instant during the motion. Okay, so there's the free body. The force is acting. There's a weight force down. And there's a normal force perpendicular to the surface. The weight force is conservative, so that's fine. The normal force is non-conservative, but the work is 0. So we can use this. Okay? So now I'm going to go instant 1 and instant 2. Instant 1 is going to be at the top of the hill. Instant 2 is going to be at the bottom of the hill. The only conservative force is gravity, so the only potential energy we need to calculate is gravitational potential energy. At the top of the hill, that's the person's mass times 9.81 times 3 meters. So that's 29.43 m. At the top, the kinetic energy is 1/2 times the person's mass times the speed squared, and the speed is 0. So there's no kinetic energy at the top. Oh, I glossed over one thing. I didn't tell you what I'm choosing as my height equals 0. Remember, you can choose anything you want as your height equals 0. I always just choose the lowest spot in the problem, so I'm calling this my height equals 0. But you'd get the same answer no matter what you chose as your height equals 0, as long as you're consistent. Okay, so the potential energy due to gravity at the bottom of the hill is mass times 9.81 times 0. So the gravitational potential energy is 0 at the bottom. And the kinetic energy at the bottom is 1/2 times the mass. We're trying to figure out the speed. We don't know it, so I'm going to leave that as v squared. And we're going to calculate that capital V. And now I'll put it into the equation. So 29.43 m plus 0 is equal to 0 plus 1/2 mv squared. And you can divide both sides by m, which means this would be the same no matter what this person's mass is. And you get that v squared is 58.86. Take the square root of both sides. And you get 7 point something. .67 meters per second. The reason that it doesn't matter what you choose as your height equals 0 in that gravitational potential energy is because potential energy only shows up in conservation of mechanical energy as a difference. And so if you chose the center of the Earth as your height equals 0, you'd have a huge potential energy at the top of the hill, an almost equally huge potential energy at the bottom of the hill, but the difference would still be 29.43 meter times the mass. Anybody have any questions about that? Okay, so I know that was like super wordy and stuff, bordering on sort of philosophical a little bit, but I tried to put a box around the stuff that you really need to remember, and you can see that when it comes to doing the actual problems, it's pretty short and sweet. So okay, that's all. Happy Veterans Day. Thank a veteran, and see you on Tuesday.